Hello, and welcome to the Gaming with Science podcast, where we talk about the science behind some of your favorite games.
Today we'll be talking about Turing Machine by Scorpion Masquet. All right, welcome back everyone to Gaming with Science. This is Jason.
This is Brian.
And today we have a very special guest, Stephen Granade. Stephen, we know from Science Track at DragonCon, which I think people have heard us talk about before. He is the lead guru and ringmaster of the Science Track and manages to keep all the things running and fight for our space and make sure we have the resources we need. So we are very grateful to him.
The Grand Poobah.
You make me sound so organized.
All you need is the illusion of organization and you're fine.
That's right.
Anyway, but if you can kind of introduce yourself to the guests, what's your background? What's your story?
So my background is that I spent my undergraduate years at a small liberal arts college as a member of the Major of the Month Club. But as my chemistry professor said, I never dropped any of the majors. So after cramming 4 years into 5, I had a bachelor's of science, dual major physics, chemistry, and then a bachelor of arts, theater arts with a math minor. And I looked around at the options there and decided, you know where the real business is? That's physics. So I went to graduate school in physics. I studied atomic cooling and trapping, where we would use lasers to cool down atoms to ultra cold temperatures to the point where they started to act in concert, and you would get basically a quantum superfluid. If you've ever heard of like liquid helium, where you cool it down enough that it doesn't have friction or things like that. We were doing that, but with dilute gases of atoms. So also, again, just a great career decision. Lots of people wanting to cool atoms down a lot. But fortunately, it also involved lasers and optics. So I moved into working for companies doing sensors and image processing, which of course turned into machine learning. So I just have this mishmash of different experiences and background.
That is remarkable. I have tried to explain laser cooling to my oldest son to no avail.
Oh, yeah, I bet.
But can you explain, how do you cool something with a laser beam?
The most straightforward way is a method called evaporative cooling that works like it sounds. It's sort of like what tends to happen if you've got a hot cup of coffee, where the liquid in there is really, really hot. And so the water molecules bounce around, and then occasionally they bounce around in such a way that one of them gets more energy and the other gets less energy. Like the overall total is conserved, but one of them gets enough energy that it can turn into vapor and escape, leaving behind cooler atoms. So we would start with just as many atoms as we could pile into a trap that was formed out of the electromagnetic potential that you could create with atomic laser beams. And then so if you could imagine the atoms are all like rolling around in this laser beam like trap that is sort of like marbles in a bowl. And then you keep lowering the edges of the bowl. And what that ends up doing is it lets the hottest atoms, the ones with the most energy after a collision, escape, and the rest of them get colder. And so then you lower the bowl a little more atoms escape with more energy, the ones that are left get colder, and you just sort of keep doing that and reducing it in temperature until you're as close to absolute zero as you can get.
You're almost like filtering out the slow atoms.
Yeah, you're making it easier for the hottest atoms after they collide to escape, carrying off more than their fair share of energy, so that the remaining atoms drop in energy and are colder and are moving less fast.
Wow. I study onions.
Hey, there is some fascinating stuff going on with those onions and all the chemistry there. You told me about this. Anyway, we usually start with some sort of fun science fact. And Stephen, as you're our guest, we give you priority. Do you have something fun you want to share?
Yes, I love collecting science facts. I think that's part of what has ended up happening with me being involved in the DragonCon Science Track, because I get exposed to all of these other scientific disciplines that I am kind of a dum-dum about. My favorite current fact is that your fingernails grow at about the same rate that plate tectonics move.
Yeah, I've heard that before. That's great. It gives such a fantastic visual representation of what's happening, right?
Well, it feels like so very different scales, because you've got the, inch-like fingernails on your fingers, and then you've got these giant plates, and they're both moving and growing at roughly the same kinds of speeds. And that's just wild to me to think about.
And yet, when I think of it like that, I think, wow, those plates are moving really fast. Because like I've seen those Guinness Book of World Records of those people that never cut their fingernails, and that's like
Oh,
feet
right.
and feet of fingernails over a lifespan. So that's more than I would have expected.
Yeah.
Jason has fast-growing fingernails confirmed.
No, I have the nervous habit of picking them. I've never let them get that long. Like if they start getting over like 2 millimeters, it's like, oh no, they're bothering me. I must get rid of them.
Yeah.
Should I do my fact too?
I mean, absolutely.
So I have to turn everything. I have a hammer of bacteria and genetics, so I have to turn everything into a nail. So what I found is it's a pretty old story, but it's not such an old idea at this point. A lot of this work was pioneered by a synthetic biologist and DNA guru George Church of using DNA to store digital information. So I thought that was appropriate for this. So DNA is incredibly dense in terms of the amount of information that you can store in a really small space, and it's also very stable. Like you can, under the proper conditions, have DNA retain that information for thousands of years, which we don't really have good storage media that can actually hold up to those long-term archival states.
Yes, although as we learned in the last episode, a chunk of amber is not an appropriate archival state for DNA.
No, it is not. No, it is not. In fact, they're even putting some archival information into living cells, so then you get the repair and replication mechanism. So they're sort of like dropping little Rosetta libraries of human information into living organisms, kind of very sci-fi. So it's great for archival. You can keep it for a long time. The problem is it's absolutely ridiculously expensive to write to DNA because you are synthesizing new DNA molecules. You're storing digital information, binary in the A, G, C's, and T's. It's actually not too bad to get it back out again because you can just sequence the information and turn it back into digital information. So that's not cheap, but it's a lot easier than synthesizing the DNA.
How do they put that together? What does the synthesis step look like?
Oh, you can actually run through a process through just from raw chemical bases, synthesize a specific DNA sequence, like from scratch, stick it in a test tube. They're always working on like new ways to do this.
Yeah, I think currently the limit's probably about 100 to 150 base pairs is all you can get in one. But then there are tricks to stitch them together. So you can like yeast is apparently very good if the ends are match up to a relatively small out, like 20, 30 base pairs. The yeast will take a look like, oh, those belong together. And they will just glue them together at that spot. And I think that's how there's a lot of stuff about making a fully synthetic genome about 10 years ago, which they did through this process of like starting from these tiny little building blocks and then slowly building it up through many, 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 many cycles of this recombination, it's called, to glue them together. And presumably many, 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 many hours of technician and graduate student time actually making this work and figuring out how to work. And figuring out all the ways it could go wrong, because they had to do things like, the other problem with DNA is it's fragile. It's literally at 1 atom thick. And so any shear forces can just rip it apart. And so the pipettes we normally use shear DNA down to about 10,000 base pairs, which is way too small for anything actually living. So they had to do all sorts of crazy workarounds to be very gentle with the DNA as they were handling it, so it wouldn't just get ripped to shreds by them trying to move it around.
Well, that's wild.
That artificial synthetic genome also has watermarks in it. They wrote their names and a poem and a couple things. They left an HTML link in the DNA of this organism. So it's really weird.
That is amazing. Biology is weird and squishes.
That's why I love biology. It's phenomenally complex. And you get all sorts of very interesting emergent properties out of it. I mean, when you get down to it, most of us are hydrogen, carbon, oxygen, and nitrogen. And they're just rearranging certain things. And you get phenomenally complex things like podcasters and plants and such.
Right.
So
yes, biology is squishy and stinky and fun.
Well, thinking back to my Orgo days, I'm like, all right, so what's the synthesis steps that gets you from pile of chemicals to podcaster?
A couple billion years.
yes.
Yeah.
So we had a previous episode on evolution. So we'll just link that in the show notes.
Nice.
Yeah, give it about 4 billion years and a whole bunch of trial and error, mostly error, and
Right.
what works will be around still. All right, but we're not talking about biology today. We are talking about computation. So let's dive into this game. So today we are talking about Turing Machine by Scorpion Masquet, which was designed by Fabien Gridel and Johan Levet. I hope I'm pronouncing those right. This is a very interesting game. Brian and I played this. This is outside our normal area. It is a deduction game. So the most famous deduction game that you're probably familiar with is Clue. The idea being that the point of the game is to uncover some particular piece of information. In Clue, it's like, okay, who did the murder, where, and with what? And the designers of Turing Machine really liked deduction games, but they saw there was one major flaw, is that usually you are asking questions of the other players. So the players all have parts of the information and you're trying to assemble the whole. But usually some information is more valuable than other information. And so some players might get an advantage just by the cards they're dealt or whatever. In Clue, this would be, I'd say probably the rooms have the most value because they're the hardest to get to and there's the most of them. So if you happen to get a handful of rooms, you have an advantage over everyone else. So I'll put in the show notes a link to the designer diary. It's actually really fascinating, all the iterations they went through over this. But they eventually hit on the idea of, well, we won't have them ask other players, we'll have them ask the game itself. And that's how we have Turing Machine. So the way this is set up is there's a central piece, which is actually unnecessary. It's just a cool little visual piece.
We need a word for that, for things that are totally unnecessary for the function of the game, but just make the game look a little cooler, or add some like fun clicky element to it or something. I still haven't come up with it yet. What did we come up with, Jason?
I think Boondoggle was the closest we got.
Yeah.
Goober, if we want to take from Spider-Verse.
Yeah.
Widget, that's probably too useful. It's too, I mean, a spandrel is actually kind of useful. It does something. So it's not just that.
Well, listeners, get in the Discord. What term is this? We are missing a term, and that's not allowed.
You know, I would have originally said those kinds of things were absolutely optional. I spent, a chunk of time playing cheap-ass games where you got basically the rules and some cardboard. Like if there was going to be a board, you'd get sort of thin card stock with it on there. And then they're like, you have dice, you have tokens, you have, chits to count up things. Just pull those from Monopoly or whatever other sad game that you should put to one side to play cheap-ass games. And I like that. I was in grad school. I had no money, but I have gotten to really like the ones where it's like, we spent a little extra money and now the meeples have a little bit of heft. You're like, oh, that's really nice, actually. Something nice and tactile about those things.
Yeah.
I'm a sucker for some glossy cardstock. I know that Jason is as well.
Yeah, no, I like the tactile sensation. And so what this central thing, it's just a hexagon with some little like 8-bit computer faces on it. It's just to organize things because the real meat of it there are 6 faces and around that you put anywhere from 4 to 6 cards, which are your condition cards. The goal of this game is to deduce a number that is hidden. And the thing is, the rulebook comes with about 20 of these. There's a website where they have like 7 million of them that they've programmatically generated. So like you're never going to run out of puzzles to solve, but you have to get it because it is a very specific setup. So you set it up, you put out your 4 to 6 condition cards that have the conditions you're testing. I'll talk more about that in a minute. And then now each one of those is tied to a verification card, which tells you information. And the way this game works is you have a set of number cards. And so you put together a 3-digit number. The digits only go 1 to 5. So there's 5 times 5 times 5 equals 125 possible numbers it can be. And you take the 3 and they're tabbed, whether it's the first digit, the second, or the third. You put them together and they have these punches in each of them. And it looks like an old-fashioned computer punch card. And they designed it so that when you put your 3-digit code together, there's always exactly one hole open out of all of them. And every 125 different ones has a different hole open. And you hold this up to the verification card and you get a check or an X. And that basically tells you that with its condition card, whether your number passed the condition or not. And you use that information to try to deduce what the actual real number is because the real number passes all of the conditions out on the table. The one further wrinkle of this is that the condition cards do not have a single condition on them. They actually have multiple conditions, anywhere from 2 up to 9, and only one of those is actually being tested. So your job is first to figure out which of the many conditions on the board are actually in use, and then to determine from those which single number satisfies all of the conditions. And the authors are very clear in the rule book that in every puzzle, every single condition is is needed. You can never just skip one and come to the answer except by luck. Like you need all of them in order to get it, which leads to some weird things where there are some conditions that can never be used in the game because like one of the cards says the number of threes. There can be 1 3, or there can be 2 3s, or there can be 3 3s. If there are 3 3s, that one card tells you the solution. Therefore, that condition will never be used. It leads to some weird stuff like that. And the best way of thinking about this can be played 1 player or multiplayer. It's 1 to 4 players. This is one where I think maybe the 1 player version might actually be the most popular because it's competitive puzzle solving. Think of it as if you were doing competitive Sudoku with a bunch of your friends. It's very much a solitaire. There's no way to interfere with each other whatsoever. Your little clues and stuff are hidden. You can play it cooperatively if you want. That's definitely an option. Or you can play it solo. And I did that a few times. And I could definitely see, we say this a lot, actually, several of these games would be good apps. This would be a great app to just pull open and do with like Wordle or Connections or Turing Machine in the morning, just to kind of stretch your brain cells a little bit. I can see a lot of people liking it for that reason.
But wouldn't you lose something without the little cards getting to pick them up and make the grid and hold them up to the thing and the sort of weird mathematical magic of how does this work?
Well, yes, you would lose the tactile sensation of it. Yes. On the other hand, you wouldn't have to have Turing Machine set up for you to play every single morning, which is difficult with cats and children. So
just the dedicated Turing Machine table off in one corner.
Yes. And there's an interesting history. So right now, the final version of the game is pure numbers. It's just you have the 3-digit number you're trying to solve. They actually tried skinning it a few different ways during development. So first, and for a long time, you were trying to find out like the number of different animals on the farm. And each of the farmhands only knew one thing, like there are more pigs than chickens, or if you add up all the animals, then they are greater than 6, which seemed like some pretty uninformed farmhands, but it was the metaphor of the game. Then, to try to tie it to Turing, Alan Turing, which we'll talk about more in a bit, they themed it as being trying to discover components of the German army, like how many tanks did they have, how many infantry did they have, etc. And at the end, they decided that, we're just going to stick to pure numbers. We're just going to make it a pure number deduction game, which I think is, I could see the skin being nice, but I really think what they were going for, they really just like the pure logical deduction. And I think keeping it pure like that really reinforces the feel and the vibe of the game they're going after.
Yeah, I feel like if this were games where you have that skin where it really, you see sort of the abstract working of the mechanisms underneath the different engines or things like that, then I want the skin to still be thematically resonant with the game. If I think about something like Wingspan, which at its heart is just you're producing more resources that you put out in the form of, eggs and things like that, and you're laying out the places for the birds and all of that, so getting your birds. The theme informs what those things are in a way that feels like actual birds and their habitats. The skinned versions you're talking about sounds more like, well, this is a thing that you're going to end up mostly ignoring and treating as abstract anyway.
I agree. I think that's why it works better as just pure numbers. Because ultimately, even though it bills itself as like the punch card computer game, it's really a game about logical deduction, and it's not actually a computer. The rule book actually says it's a proto-computer, but I guess whoever was in charge of the box wanted it to say it was a punch card computer game.
Right.
And it does feel a little magic to put all the punch cards together. There's always that one hole that's open and you get to look through and get your answer. And Brian, I've known this for several weeks and I've hold off playing. Like I figured out the magic for how that happens.
The mathemagic?
The mathemagic. They describe it very clearly in their design diary, and it turns out to be really, really simple.
Okay, I'm excited to hear about it. But you made a point when we started this endeavor. We can't just do biology games. We have to mix it up. In the whole idea of STEM, science, technology, engineering, and math, this is a math game. That is what this is, right?
I don't think there's a lot of those out there.
I don't think so. Well, where they just completely go for it. It's like, it's fully abstracted, just numbers. We don't need any theming.
Right.
Okay, now explain to me how this works, because I want to know.
So when I first saw it, I was like, oh, I thought this would be like Spot It or Dobble, which I saw a video on a year ago. I'll link it in the notes. In Spot It, you have this collection of cards, and every pair of cards shares exactly one symbol. And there's this whole mathematical thing to ensure that happens. I thought it'd be something like this. So every trio of cards would share exactly one hole. And then it explains like, oh, you take all 125 numbers, you put them in a grid, and then you randomize them. And then you just take whichever card. So this is the first digit, and it's a 1. So all the ones that have a 1 in the first digit have a hole in them. And all the ones that have a 2 in the second digit, when you go into that one, you put a hole in them there.
It's decimal encoded. It's decimal place encoded.
Basically.
Oh, that's super cool.
The first versions, they actually had them in long strips because they were all adjacent to each other. They later realized it was actually much more fun when they randomized them. And so that's what we have the final one. So there are basically 125 spots on the card where there could be a hole. Anything that matches the digit of that card has its hole punched out. And so by definition, when you put all three of them together, there's only one hole left open.
So you have like all of the 500 numbers punched on the 500 card and all of the like 30 numbers that have number 3 number on the 3 card in the middle. Yeah, that's really cool.
And it's not completely random. They did put in some rules because, I mean, you could do this like a bajillion different ways. So I think what they did is they just generated a bajillion different ones and then they screened them because they wanted to make sure, okay, nothing has more than 2 in a row. You don't form any weird angles that might catch and tear. And the end result actually looks a lot like an old-fashioned computer punch card because you all have these like 1 and 2 slot holes all next to each other and they're all spaced out and in different directions and stuff. And it looks really cool. And I think you were about to ask Brian about the numbers. So there's 125 possible codes.
Yeah.
They're laid out in a 12 by 12 grid with some of the corners left off for some symbols you use to match it up. But I think there's 133 available slots, which means there must be 8 squares that are just never used.
And that must be things like the 333, right?
No, 333 is a valid number. You'll have a hole going through it there. It could be a valid code, just not with that one card. It could be a valid code for a different set of cards.
Oh man, yeah, I'm over my head, but that's okay. That's okay. I'm gonna stick
I wonder
with
if they added some blank ones so that they could ease the constraints of making sure that you wouldn't have cases where there were weird corners you could catch on or they were too close or things like that.
Maybe. I suspect it's just that a 12 by 12 grid is the smallest square grid you can fit 125 different numbers on. And so they just worked with that. In the early versions of the game, it was actually a 4-digit code you were going after. And they dropped it down to 3 because it let them have smaller number of holes and bigger holes. So it worked out better. It was like bigger symbols, bigger holes, fewer of them. So that worked out well. They also used to have a lot more esoteric conditions. So now it's like, oh, the sum of these is equal to 4 or greater than 4, whatever, or this is odd, this is even. It used to be things like all of these things multiplied together are this, or this is a prime number, or other much more mathematical things that the publisher said, nah, these are too esoteric.
That's one non-prime digit.
Exactly.
So they wanted to make sure that the conditions were things that didn't have too many assumptions about mathematical knowledge other than odds and evens, bigger, lesser, things like that.
The thing I want to know still, though, is that there are 48 condition cards. Each has at least 2 conditions on it, and many have more than that. But there's only 95 verification cards, which means some of them have to be pulling double duty. And I don't know how that works. That's the part they actually intentionally did not explain in the designer diary. So they left that one a mystery. Anyway, that's the game. If you like Sudoku, you will probably like Turing Machine. That seems to be the pattern from what I've gotten online. If you want to check it out, definitely watch some videos. It is not intuitive to most people the first time around. But once you get it, it's like, once I figured it out, I was like, oh, I get it. Then I could do pretty well about 90% of the time. And then I'd forget something and make some stupid mistake and completely mess it up.
I mean, when we played once on normal difficulty. We both did great. We got it on the same round of guesses. I think you used 1 fewer piece of information, no issues. We clicked up the difficulty 1 notch, and we could not solve this code. We both screwed it up multiple different times, right?
Oh, I know where I messed up.
Okay.
We had one of the ones where there were like 6 different conditions, and I misinterpreted my result and thought I had eliminated 5 of them when I'd actually only eliminated 4 of them. And so I was going off of wrong information. All right, so that's enough about the game. Let's move on to the science. And Stephen, I'm hoping you can help fill in the information here, because although I work in bioinformatics, like I'm not a computer scientist, I'm not heavy into that. I want to start with the namesake. So this is named after Alan Turing. It's a Turing machine. So who was Alan Turing and what was his machine?
So Alan Turing was a British mathematician and ended up founding a lot of like fundamental thought about how digital computers would work. He was doing a lot of this work in the 30s, and then of course in the 40s got swept up in the race to crack the Germans' Enigma machine that they were using to encode secret messages, where a lot more sort of approaches to and tactics about doing digital computation computation occurred at a point where there were no general purpose digital computers. Everyone was having to do analog circuitry and wind things together. But what Turing did was reason mathematically about how these computers that didn't quite exist yet might work. And he came up with a mathematical model that I believe he called it like the A machine, and then it later his advisor renamed it to be the Turing machine. But it was, rather than an actual machine, sort of a mathematical model, a thought experiment about how digital computers could work and how you could describe a system that then you could do mathematical reasoning about, because Turing was really interested to dive into the question of like, are there problems that a digital computer can't solve? He was playing in some of the same kinds of areas. If you've ever heard of Gödel and Gödel's conjecture that there are axioms in any mathematical system that cannot be proven, you can never have a perfectly self-proving mathematical system. There's always going to be some axioms that you just sort of have to assume as first principles.
And a bit of vocabulary for listeners, axiom is basically the foundation bedrock of math. They're the things you start as like, okay, we know X, Y, and Z. From that, we can derive other stuff. Your axioms are that first bedrock stuff you lay down.
It's also the ship in Wall-E.
It is also the ship in Wall-E. So Alan Turing was trying to look for some of those same kinds of principles in these digital computation machines that, don't exist yet. So he came up with a system. The idea is that you've got this infinite roll of tape that can be slid forwards and backwards underneath this little device that is looking at each little cell on the tape. So the tape is divided into regions, and you've got this device called a head that can look at one of the regions, and it can read the symbol that is written there. It can write a new symbol on there, and it has this set of rules called states that say what it does when it encounters a given symbol. So you could imagine, for example, a 4-symbol tape. You can have A, B, C, or D on one of these cells. And so when it looks at, say, an A, it says, okay, move the tape 1 cell to the right. If it sees a B, move the tape 1 cell to the left. If you see a C, write a D. If you see a D, don't do anything. So now you've got a simple set of rules for moving the tape around and manipulating these symbols on the tape. The next level up is you say, okay, those are the first set of rules for A, B, and C. But if you see a D, now you're going to swap in a second set of rules. You're going to go to another state in the state machine. So it shifts a new set of rules about what it does with A, B, C, or D. And maybe there's a third set of rules and a fourth set of rules. So it can swap in and out these rules depending on what symbols that it sees. So it could have a case where it says, all right, an A says I move left, and then a B says I move right. But if I see 2 B's in a row, now I'm going to change my rule. So now that B means I shift it to the left. So it's simple sounding, but abstract. But it turns out that given those operations, you can simulate any computer algorithm, like top to bottom. They can get really complex. You can build up a whole set of symbols and a whole set of these rules, these states that the machine swaps in and out. But you can use that to have any digital algorithm, you can describe it using that machine and the proper set of symbols and rules.
Do our computers work like that? This is one thing I've never been able to figure out. Like, is the Turing machine an abstract concept, or is this essentially the foundation on which all actual hardware is built?
It is an abstract concept because it turns out, number one, if it's going to be an actual Turing machine, the tape has to be infinite. If
okay,
you
the
only
minor issue there.
It's a small wrinkle in building one of these things. Yeah, because it turns out if the tape is not infinite, let's say it's just merely super, super, super big, like you've got a Google's worth of cells, there are some algorithms you're not going to be able to describe. So it's more that it was simple enough that you could do mathematical reasoning about it and create mathematical proofs to answer some of the questions that Alan Turing had about how digital computers would work.
This almost seems like in biology, we have our model systems, which are like our little, like the lab mice and the E. coli bacteria, which have been like, they're very simple, they're very reduced, but we can do a lot with them to try to understand how things work out in the real world. Is that kind of this for computation? It's a very simplified model system that you can find out some rules and then apply that out into real computers.
Yes, you have stripped the idea of a digital computer down to like the fewest things that you can get away with and still be able to describe all of these different algorithms.
Okay. And in looking up research for this episode, I ran across a phrase called Turing complete, which apparently describes something about computers, but I couldn't figure out exactly what. What is Turing complete?
So if a device is Turing complete, it means that it can do all of the digital operations necessary to express these computer algorithms. So if you have a device that is not Turing complete, you are limited about the kind of algorithms that you can use, that you can describe with it, that you can, create on this device. If it is Turing complete, then it matches the same characteristics as this hypothetical Turing machine and should be able to express any digital algorithm that you can come up with.
Even though it doesn't have an infinite stretch of
Even though
tape.
it doesn't have an infinite tape. Yes. Yeah. Thankfully, they managed to figure out how to do it without infinite tape.
I think anytime you need infinity, maybe it becomes very esoteric and abstract as soon as
Listen,
infinity
I
has
come
to be
from
invoked.
physics. We ran into infinities and we're like, you know how you get rid of those infinities? You divide them by other infinities. And we will call it renormalization.
So it sounds like most of our digital computers nowadays are Turing complete. At least, like for me as a user, it seems like they're capable of running basically anything we want on them. Is that right? Like, is my cell phone Turing complete?
Yes, it has all of the operations necessary to create these digital algorithms. You end up being limited by the amount of memory that you have available, whether that's memory where you can shove all of the numbers that it's operating on in working memory or to store it onto a disk or other medium. But it's able to do all of the operations that make it equivalent to that Turing device.
Got it. So essentially, Turing complete in theory. In practice, like storage becomes an issue. But in theory,
Right.
What's not Turing complete then?
Yeah, like what's an example from modern life of something that doesn't qualify?
I really should have looked up this because at this point, I'm not sure we've got a lot that isn't Turing complete. The fact that you can, run Doom literally on your toaster. It's computer chips have become so cheap and so readily manufacturable that it is, I think, harder to get a device that is not Turing complete, at least on the computer side. A lot of this came out of the point where, as I mentioned, they were building computers using analog circuits, and there were a limit to the numbers and kinds of operations that you could create by, winding resistors and getting capacitors and soldering them all together. So I think that was a much bigger barrier when you're talking about the 40s with, the early steps of digital computing with the UK's bombas that were working to crack the Enigma code than it is at this point where computer chips are super cheap and super easy to get, and you just don't do much in the way of analog computing anymore.
So I just did a quick search on this and pulled up the Wikipedia page, and apparently I think you're right because there's a list of things that are accidentally Turing complete, which includes stuff like Microsoft Excel, Minecraft, and Magic the Gathering.
Yes.
Wait,
Yes.
I'm sorry. What does that mean?
That means you can run computer programs in Magic, and I have seen the YouTube video that explains how to do so. I'll link it in the show notes.
Yes, please put that in the show notes.
You can do it in Excel with its formulas. You can create basically computer systems in Minecraft using the redstone bridges and the linking them all together and the switches that they've got available. You can create the different kind of logic gates that are required to build up to more complex mathematics.
But Magic the Gathering too, somehow.
Yes,
you can design loops in Magic.
Yes, you can. It's the world's most boring game of Magic, but you can do
it. So when you were talking about the Turing machine, the analogy that you made, you had a read head and a write head, a long line of tape, symbols. I mean, all this sounds like magnetic tape. That's not a coincidence, is it?
No, and it gets to the thing you were talking about earlier about like, how do you store information? Turing's machine, his mathematical model, used a symbol table, and you could have 4 symbols or 5 symbols or things like that. But it turned out that it was a lot easier to build up these systems if you just have 2 symbols. You have true and false. You have 1 and 0, and then you start building those up from there. And it turned out that you could store this in the direction prediction of a magnetic moment. If you think about the little old bar magnets where you've got a north end and a south end, you can say, all right, if the north end is pointing up, that is 1 or true. If it is pointing down, then that is 0 or false. And you can encode that on a magnetic tape by having the ferromagnetic particles where you hit them with a magnetic field to flip the direction that they're in, and then it persists at least for a while. Eventually, the magnetism sort of wears off depending on, if you leave a tape in your hot car when you're, 10 and then come back a month later and discover that it's all kind of gone.
Yeah, but so tapes weren't actually the first one, though. And this plays right into the game because the game has the whole punch card thing. And punch cards were among the first actual ways of storing information. They're not digital like magnetic tape, but from what I was reading, like the code cracking for World War II, they were generating like 2 million punch cards a week to try to run all their computational stuff. Have you ever run a punch card computer?
I have not, but I have used punch cards in the ways that they were never meant to be done, because I was in a laser lab at a university where the professor had gotten what was probably multiple graduate students' entire PhD researches on punch cards and then taken them away because they have little holes in them. If you're trying to align a laser beam, it's really nice to have a place where you can have a little hole and pull it away and a little hole and pull it away. So that's what we used our punch cards for.
Oh my, those poor graduate students. They're probably,
I know.
Hopefully they weren't dead, but if they were, they probably were rolling over in their graves.
Yeah, I used to be pretty blasé about the fact that we were using ex-grad students' graduate life work basically as a cheap way to not have to use a hole punch on cards. I was like, whatever. But then I sort of realized what that felt like because we were doing atom cooling and trapping, and there was a lot of race to try to be the first group to create a Bose-Einstein condensate that had been predicted by Bose and Einstein back in like the 30s. And it was this giant effort. People couldn't get it to work and eventually did in like 95. And it was impressive enough that they were getting Nobel Prizes for it in 98, which is just a ridiculously fast turnaround for that. And then like by the year 2000, it was a very common undergraduate lab. Like everybody was making those Einstein condensates in the lab, just, over 2 days. It's like, okay.
Nobel Prize to undergraduate laboratory exercise in a couple of years. Amazing.
Yeah. But no, when I was looking up the punch card things, I did not appreciate, I understood that punch cards were used to program computers back in the day. I didn't appreciate they were data storage. They were the floppy disks of their day because there wasn't actual permanent computer storage. And so you'd have all these punch cards and they had to be read in order because you flip 2 of them, you completely mess up the program, you mess up the data. And so they'd have these big stacks, they'd have like Sharpie lines on them to help you figure it out. And multiple places I found something to the effect of woe betide the graduate student who dropped their stack of punch cards and they just scattered everywhere and you had to try to figure out how to get them back in order.
Were they not numbered?
Well, originally they were just like long pieces of cardboard with a row of numbers and then, multiples of those rows. And they would be punched by hand. And then later they would type in the thing that you wanted and it would encode it into the space of the punch cards because it's spatial information storage in the same way that the game is storing information about the numbers. Each of those cards, for example, has the position of every number that starts with a 3, every 3-digit number that starts with a 3 is encoded by holes positionally punched on those cards. And I think because you would end up with just like stacks and stacks and stacks of them, because it was not a very information dense way of storing that information. You had bunches of them and it took a while to get to numbering them. You would occasionally have ones that were a certain statement or operation that would be pretty common, like adding 2 numbers or, moving information around. And so you could have punch cards that were commonly created that you just be like, oh, I need one of these perhaps, instead of like, I'm going to hand create every single one each time. So yeah, I think there were some quality of life things that people had to come up with, like numbering them.
Probably via lots of pain. Because that's generally what happens. Like someone messes up like, oh, I should have done that. Let's do that from now on.
Yes.
Oh, I'm sure I'll never drop it. It'll be fine. I'll be careful.
But the history of these things is fascinating. I didn't realize, I think about them with the 50s. So apparently the first wide scale use was in the 1890 census because they're like, it's going to take us 15 years to tally the census we have to do every 10 years. Like, this is not going to work. And there's someone who came up with a punch card system that you could just count. It was all it was doing was tabulate. It was counting stuff, but it made it so they got it in like 3 or 4 years. So super fast relative to what they thought. And that guy formed a company that like 3 or 4 name changes later became IBM, International Business Machines. Which is still around. And that's a pretty good record for a company, I think. And if you go back further, like the first one that everyone brings up is the first punch card, like proto computer thing was used for weaving.
Yes, the Jacquard loom.
Yeah, it would determine which parts would get lifted up and which parts would stay down. So you could make patterns and you could make them reproducible. Some version of this is what powers the player pianos you see in the old Westerns, where they've got all the holes in the circular paper that's determining which keys get put. Okay, in the grand scheme of technology, 200 years is not a long time, but it's way older than I thought it was.
Yeah, folks started to realize that you could encode information in holes in paper much earlier than you might imagine, especially if you're used to thinking of, yeah, computers are the things that kind of came out of World War II and then really got a jump start during the space race. And they're like, oh yeah, Jacquard looms were creating patterns for weaving that you would just bolt onto the side of your loom and have it do operations based on the holes in the cards.
So, stupid question. Is a player piano Turing complete?
I do not believe so, because it is not doing any operations. It has no ability to swap rules in and out. It's just when this hole comes by, I press this key.
I think a player piano is basically read only.
Yeah.
Okay. So that is a key difference. You can program something that can just read. So a music box is programmable, but it has no ability to change what is on the recording, right? You can't write, you can only read. And that's the key difference.
Yeah.
Okay, cool. Yay.
Now I'm curious if there are any Turing complete devices that would be read only. And I don't know. I guess if it's an infinite tape, maybe you can get away with it, right?
Hey y'all, quick aside here. So after we recorded this episode, I looked this up and it turns out that while you can have a read-only Turing machine, it is not Turing complete. Some operations just can't be done when you can't write to the tape. So just want to put that in here so we had the answer. And now back to the show. We probably actually need to start wrapping this up. This has been a great conversation, but there's a few things I want to touch on before we do. One is the great mystery of computers to me. How do you do math with just ones and zeros? You talked about how it's much easier to do all these operations if you just use on and off with the magnetic fields. But when you get down to how those actually mesh inside the CPU and are doing math and are doing the calculations that show what's on my computer screen and all that, I do not understand how that works. Like, what is going on there in the guts of the CPU?
If you go all the way down to the base level, you're looking at Boolean algebra that was created by a mathematician named Boole back in, I think, the 1890s, where he was looking at what kind of algebraic operations you could do if you had just ones and zeros. There's more to it, but for our purposes, let's just stick with ones and zeros. So every number is a 1 or a 0, and you can stack those together. So in decimal, where we would go 0, 1, 2, 3, 4, 5. Instead, you go 0, 1, 10, 11, 100, 101, 110, 111, 1,000. So it's more properly base 2 numbering where we're used to base 10 numbering. And then you introduce 3 operations. You introduce and, you introduce or, you introduce not. So if I have 2 one-digit numbers that can be either 0 or 1, if I and them together, the result is a 1 if both of the numbers that you started with is 1. So if I have a 1 and I have a 1 and I and them together, I get a 1. If I have a 1 and a 0, if I have a 0 and a 1, I have a 0 and a 0, I get a 0. So both the first number and the second number have to be 1 to give you a 1. The OR operation is like that, but it's a little more permissive. If one of the numbers or the other number is 1, then it results in a 1. If both of the numbers are 0, it results in a 0. And then the not operation changes the number. If you have a 0, the not of the 0 is 1. If you have a 1, the not of the 1 is 0. So you can start to take those operations and you can take longer numbers. So you can and 2-bit numbers together. So like an 11 and a 10 added together gives you 10 because the first digit is 1 on both of them, but on the second digit, only one of them is. If I OR a 10 and 11, I get 11. If I take 10 and I not it, I get a 1. So you can build up longer stronger algorithms using only those three operations, and, or, and not. There are algorithms that let you start to create, for example, addition. It lets you create multiplication. If you want a really deep dive into this, I'd say go look up a YouTube video describing how the half adder, HALF, half adder algorithm works for adding numbers together using just bits and ands, ors, and nots.
It sounds like we're back in the Turing machine territory where you've got a very simple setup, and then through this like layers and layers of complexity, you manage to build up to something that we would recognize.
Yep. Yeah. So that like computers don't natively know how to do division, but we've got clever algorithms that let the computers do operations that result in a division that are stacks of these logic gates, they're called ands, ors, and nots, and rules about how you apply them.
Okay, well, thank you. Brian, do you have any last questions or comments you want to put out?
I have my one joke about binary. Well, you've probably heard it before. There are 10 types of people in the world. People who understand binary and people who don't.
Now, the really fun thing, as somebody who came out of laser cooling and trapping, one of the things that people end up doing once you can start to manipulate these atoms in their quantum states is they start to build quantum computers where you have qubits, Qubits, where they are particles that are in a quantum superposition. So maybe they're both one, maybe they're both zero. We're not going to know until we actually make the measurement. And all kinds of wacky algorithms are possible once you start to have enough qubits together that you can do, in effect, kind of parallel probabilistic computation.
I hear about those every now and then, although my understanding is that they're facing the infinite tape problem in that last I checked, like they can get like 15 or 20 qubits, maybe 50.
There are systems where you can have more of them, but they're not in sort of the classical superposition. There's this thing called an Ising state about where you can get atoms in a crystal aligned properly in ways that let you do some aspects of quantum computing, but not the ones that people are really both interested and afraid in, like breaking cryptographic numbers really, really fast so that all of your banking accounts can be sucked dry.
Yes, that's mostly what I hear, is that if we manage to get quantum computing to work, all our current encryption goes to pot.
Yes, that is the headliner application for it.
All right. So Brian, you have your nitpick corner. Do you have any nitpicks about this game you want to bring out?
I mean, it's not a computer. So that's kind of a thing. Like it says it's the punch card computer, but it's not really a computer. I don't know what it is, but it's not that.
It's a proto-computer. The rulebook clarifies.
What does that mean?
I don't know.
Yeah, I guess it's using like computer-like storage or encoding of information, but there is no computation going on. It's sort of like the old school version of computers, which were people who did computations. You're the one doing the computation by putting them together.
That's true. We are the punch card computers.
You are your own Turing machine. Congratulations.
I have two nitpicks, and these are little ones, but one is it's a 4-player game, but they only include 3 sets of the number cards. I assume that's a cost-saving thing because they seem like they're either very nice cardboard or maybe very thin plastic. That's probably just a cost thing because I assume custom punching out all of these different numbers is kind of expensive. The other one is actually, recently you talked about the hardest thing about a game is writing the rule book, because by the time you get to that, you know it so well, you don't know how to explain it to a newbie. I think that happened here because nowhere in the rule book do they actually say, by the way, the code you're looking for is the one that satisfies all the conditions on the table. It sort of alludes to that in 1 or 2 places. It kind of assumes you get that, but it never actually says that outright.
No, I actually got that from watching a YouTube tutorial. It's like, by the way, if you want to play this game, you need all of the condition cards.
So that's my nitpick, is like, that's a fairly important part of the game that I think they left out of the rule book and probably needs to be corrected.
Gosh, yeah, that's a great point. So my dad was a historian, and his specialty was Civil War. And so he would play the Avalon Hill game Gettysburg with his classes. And so I grew up with this Avalon Hill Gettysburg game, which had all these pages of densely typed rules, and they were all subsections. So you'd like, according to 3.2.7.1.4, when it is muddy, my terrain modifier is such and such.
Oh, no, this is Stellar Horizons.
It's a game written by an engineer.
All right, so let's get on to letter grades. Brian, throw this to you. What do you think about gameplay?
I don't know. this is a weird one because this isn't the kind of game that we would typically play. But if you just like want to play a light game or something, I kind of agree with you. This might be the one game that's worth having in solo mode where you just set it up every once in a while. I guess I'll just give it a B. I think it's kind of its own little unique niche. There's nothing really competing with it.
Yeah, apparently there's this whole genre of deduction games I was unaware of, so there might be some others competing with it. But like in our sphere, no. I'm going to give it higher. I'm going to give it an A minus, and I'm going to give it that because for what the game sets out to do, I think it does very well. The only reason I'm getting a little lower is because I think there's a barrier to entry that can put off a lot of people. In fact, when I was doing research, I ran across a Reddit thread by someone who's a professional game explainer who is basically asking for help because no one ever understood Turing Machine the first time he explained it to them. And so he's asking for help, trying to figure out how to explain it better to people. And usually by the second or third time, they figured it out. But he just had trouble with that. And I wish they'd made that barrier to entry lower. But once you get past it, I think it can be fun. And if this is your jam, then I think it's a great game. It's not my jam, but I can definitely see what the appeal would be.
Does it have quick start rules like, hey, play this puzzle, these ones, let us explain how this works? Does it do that? I don't think it does. And that honestly, just like here, let us walk you through a simple puzzle.
Yeah, it gives an example round, but it does not walk through an entire game deduction. It gives examples of the components, but it never puts it all together until like, oh, this is your first game of Turing Machine, so you understand how it works.
This is the perpetual challenge when you have experts trying to talk to amateurs, right? It's very, very difficult to keep that beginner's mindset.
But like I said, overall, I think for what the game sets out to do, I think it actually does it very well. Especially we talked about the lack of skinning it. It's like it's a very pure, this is a logical deduction game, and there's very few bells and whistles around it. It is trying to be a logical deduction game, and I think it does that great. Stephen, do you have thoughts? I mean, you didn't have a chance to play it because we're unfortunately too far apart from each other.
Right. I did get to watch some of the aforementioned YouTube videos. I really admire games like this that can pull off an experience without a lot of the sort of what I think of as traditional skinning and other elements of it to add to the experience. You know, if you think about like bluffing games like Sheriff of Nottingham or something like that, like part of the fun is pretending to be the people smuggling the food in and out around the Nottingham Wood. Here, it's just numbers and operations. Like you mentioned Sudoku, like you mentioned Wordle, I think when that kind of game is done well, I really admire it because I think that feels to me like a much harder lift to come up with something that is that abstract and still interesting. That doesn't feel like I am playing Excel, the spreadsheet, as my game tonight.
Or Magic, the computer game.
Yes, Magic the computer game.
It still is a pretty game, but there's no fluff. It is what it is.
I mean, the punch cards, they did a little bit of fluff there, but not very much. I mean, the randomization is really the only fluff component there, and that's mathematically equivalent to having them not randomized, so you might as well do it.
Yeah.
And a hexagon of unnecessary little visual faces.
There we go. That is the one unnecessary aesthetic thing they put in there, is the hexagon. Actually, many of the people who play it single player apparently don't use that. They just lay them out straight in a row. So on to science.
How do you grade this? It's math.
I'm going to give the mathematical answer and say that the science grade is undefined.
Nice.
This game is not trying to represent any scientific concept, which I don't think we fully realized when we picked it up and put it on the show schedule. It's a game of logic and deduction. There's not a scientific process it's trying to represent. And so I don't think it's fair to give it a science grade because that's not what it's doing.
Yeah, it's like, again, it's in STEM, science, technology, engineering, math. It's math. So we can give it a math grade, and it did math.
Yeah, it feels like it is touching on some of the tools, the building blocks that you use as part of scientific inquiry. The idea of like, if I've got a system, how do I query it? What questions should I be asking? How do I get information out of this system that I'm dealing with? And it is very much in that case a toy model, but it's an interesting exercise, I think, to go through to force yourself to do that in this constrained environment.
That's an interesting way to think about it. Yeah.
I hadn't thought about that because I often say that science is the world's biggest game of guess and check. That's what we do when we make a hypothesis and we test is we are making a guess and we're checking to see if we're correct, which makes it sound bad, except that the alternative is guess and not check. which is
Right.
what a lot of other things do. So yeah, I hadn't thought about it. You're right, because there's some conditions, you don't know which. You make a hypothesis of your number, you check it to see if it actually fits or not, but you only get partial data. You have to figure out. That's actually really cool.
Mm-hmm.
I hadn't thought about that.
There are some examples of logical deduction in biology. Again, we were talking about it with the grid, right? We figured out by pure principles that to be able to code for 20 amino acids, that you'd need to have at least 3 digits to do it.
Mm-hmm.
Because you can't do it with 2. So the smallest number would have to be 3, which means we've got more options than, like, that was just sitting down and thinking about what made logical sense.
Well, there's another tie back to Turing. So he came up with what's called a Turing pattern, which is basically you have these very simple rules about things that are like making some molecules, usually at least 2 different types, one of which has a different lifespan than the other, and they diffuse out. And from very simple rules, you can get super complex patterns. Everything from like cheetah spots to fingerprints to the folds of the human brain are thought to arise from these Turing pattern processes. I'm actually studying one in corn right now where I think that a Turing pattern is involved in how this certain feature comes out.
Oh, that's neat.
Science is really fun, actually. Like, I was joking about onions, but like they are interesting too. Corn is interesting. Everything is connected.
All right. Well, that's where we should probably wrap it up. Stephen, thank you so much. It's been wonderful having you on. Thank you for teaching us about laser cooling and computational operations and all sorts of stuff like that. And it didn't come up here, but I'm going to link in the show notes what I think is probably your greatest and most lasting contribution to the field, which is the Science versus Movies panel at DragonCon. Which, for those of you who haven't seen this, there's no real science in this panel except by accident. It's where Stephen makes poor scientists suffer through some of the worst science shown in Hollywood and then explain why it's right, actually. And it's hilarious. I'll throw some links in the show notes. They are totally worth watching.
Have you done the core? Did you subject people to the core? You must have done
I
the
have
core.
subjected people to the core.
Okay.
So, Stephen, if people want to find you, where should they look you up?
So you can search for my name. I have the Google search for Stephen with a PH, Granade, Granade. My website is stephen.grenades.com because one of the French branches of the family that are out in California got grenade.com before I could. But I got my revenge. He ended up having to link to me early on where he was like, yeah, you're probably looking for this Stephen Granade.
All right. Well, then we'll call it there. Thank you, everyone. Thanks for listening. Have a great month and happy gaming.
Have fun playing dice with the universe. See ya.
This has been the Game with Science podcast, copyright 2025. Listeners are free to reuse this recording for any non-commercial purpose as long as credit is given to Game with Science. This podcast is produced with support from the University of Georgia. All opinions are those of the hosts and do not imply endorsement by the sponsors. If you wish to purchase any of the games we talked about, we encourage you to do so through your friendly local game store. Thank you and have fun playing dice with the universe.